I'm John Wolfe with Mullarney Technical, and I contributed very little to this year's presentation. I hope you enjoy it.
I'm Alasdar Mullarney. At Mullarney Technical, I'm the junior partner, odd use of the word. What it means is that I get to do the work, and John gets to critique it. I don't recall playing chess since learning the moves from my father in my early teens, but I jumped at the challenge. Am I a modeler? A sheet of paper and a pencil, and we're off to the races. Clearly, pieces are subtyped into ours or theirs and have associations representing threats or maybe opportunities. They have to be associative classes so that we can attach a value to them. And I guess I subtyped them because the threats could be potential or real, depending on whether they were blocked by other pieces. Luckily, I lost that piece of paper. I thought to take a glance at Wikipedia on chess programming, and that's not how they do it. They build trees of moves with subtrees of possible responses. Let's try that. The first insight was recognizing that we have the burden of representing ground truth of the board. Without that knowledge, how can you reason about moves? The next insight was recognition that we can fool light chess by postulating our next move and asking it for the legal moves, which of course would be those of our opponent. Okay, that's easy. Just iterate over all possible moves and all possible responses. As I watched Verifier grind through its evaluations, I wondered about scalability, and I was not the first. Claude Shannon, the father of information theory, in 1949 made this reckoning. In a typical chess position, there are about 30 moves, and so 30 responses. That gives us 30 by 30, 900, say close to 10 to the 3 variations. And a typical game lasts about 40 moves, so we're up to 10 to the power of 120 variations. And at 1 variation per microsecond, he calculated that's about 10 to the 90 years. So I got some recursive evaluation to run painfully slowly in Verifier, but my class model left a lot to be desired. This is not modeling. This is just a chunk of recursive code rendered in OAL rather than C++ or whatever. I decided that I wanted to see a class diagram that had a notion of pieces, squares, open or occupied, moves as associative classes related to players. This is chess, not tree of nodes. I also wanted to reject what I had seen in the exhaustive process, too many repetitive evaluations of uninteresting moves. More on that later.
My recollection of chess is even more distant than Alasdar's. I remember playing the game in grade school during recess. And you know, 2 evenly matched third graders will never finish a game during a 15-minute recess. So for us, the winner was determined by the value of the pieces taken by each player.
That pushed me towards modeling the game along the thought process of a human player. Here's a quick summary of the evolution of this modeling effort. As humans, we look for gain, or perhaps a retreat from danger. So to start with, let's just model those moves that have the potential to capture an opponent piece, and pick the most valuable. By the way, it turns out that automating a tactic like that, simple but carried out ruthlessly, can make quite an opponent. Playing against my bot, I make what I think is a safe move with a pawn. The bot thinks for a moment, and a bishop comes sailing in from 6 squares away, and there goes my rook. It never misses an opportunity to strike. Obviously, we don't want to capture a pawn only to lose a queen. So the next step is to look at the exposure to loss as a consequence of a given move. To do that, we lost light chess for our opponent's legal moves as we hypothesize each move of interest. Then we look at the highest value of our pieces that could be taken. As I watched how games played out, I realized that it was sometimes more advantageous to seek safety for a vulnerable piece than to attack. So the value of our most vulnerable piece was tested against the value of the most rewarding attack move. There are times when there is no apparent advantageous move, so time to play a safe move, give that pawn in the corner some action perhaps. And that's as far as we've got with our world-beating strategy as of now. And by the way, knowing which are safe squares for refuge requires keeping track of the opponent's legal moves. And there's at least one interesting twist. A square diagonally ahead of a pawn is safe until it isn't. If you move a piece there, the pawn gets the right to move there. As I mentioned, the initial effort added just two classes, piece and square, in a new board package, and a mess of OIL in the game state model. The next class model turned out to be pretty close to what is now evolved. It seemed intuitive to partition squares into occupied and open. Remember, we sometimes need a safe open square to run to. A piece can make a move as an associative class to a destination square. Capturing an opponent piece of that destination square is not open. And of course, vacating the square that it had occupied. We have the obligatory specification classes to characterize the pieces, and each piece belongs to one of two opposing players. Sounds like chess, no?
This all made sense, but for some reason, I really wanted the class model to make it obvious that each move begins on an occupied square and finishes on some other square, either occupied or vacant. But this makes for a very odd usage of the phrases on the resulting associative relationship. Instead of reading the phrases from one associated class to the other, as we normally do, each of these phrases must be read from the perspective of the associative class, back down to one of the associated classes. This seems weird, so probably we have abused this construct. Has anybody else ever run into this one? Eventually, we decided that there were really two different flavors of move. One that is currently being evaluated, and one that is merely a potential move. Only our bot's moves are ever evaluated, but both our bot's moves and those of our opponent are represented in the instance population for move. This subtyping seems a bit odd, but it is driven by our desire to keep this particular domain completely ignorant of the rules of chess, as the knowledge of what constitutes a legal move is provided by another domain, Lichess in this case. Maintaining the instance population of moves to be evaluated involves handing Lichess a list of the moves that have occurred since the beginning of the game, to which Lichess replies with a list of the legal moves available. To evaluate a potential move for our bot, we must first tell Lichess that we've made that move, so that we can see the list of moves available to the opponent in response. We use an association to separate these moves that are engendered by a move under evaluation from all the rest of the moves. And we use a different association to indicate moves that have been invalidated by a move that is under evaluation.
Recall that when running my initial brute force version, it tried my patience to see the same uninteresting evaluations repeated over and over again. We don't want to keep asking that pawn in the lower corner if it wants to take one step or two steps when all the action is in the middle of the board. So I gave the move class a state model. After evaluation, it enters a dormant state in which subsequent evaluate events are ignored. But if circumstances in its field of vision change, a reachable square is occupied, for instance, a reactivate event wakes it up again. Actually, the current strategy of limiting evaluation of moves to those which target opponent squares so limits the number of evaluations in a game that this optimization appears to be of little value. All along, we had hoped for an opportunity to showcase concurrency in the model. Well, given a state model, each hypothesized move instance can evaluate itself independently. This does, however, raise some issues in respect of maintaining ground truth. The bulk of ground truth representation is shared across all evaluators, but each evaluation does involve a delta from that ground truth. A given move may render other moves invalid in its context. We may be evading a capture move, for instance, or may allow new legal moves. Consider nestling up too close to an opponent pawn. We use two associations to segregate those instances pertinent only to a single evaluation. To sum up, I looked at two approaches and decided to pick one that emphasized modeling in the application context, chessmen rather than graph theory. For strategy, I first modeled an impatient third grader capturing the most valuable piece available. I then moved on to consider net gain and defensive play, and finally threw in a nod to concurrency.